And now, we will tackle about MID definitions. Hi, we will tackle about MIB definitions. Now that you know what a MIB is and what it contains, let us take a look at how the information that goes into a MIB is defined. The management information in MIB is effect represents data. The data reflects the state of the device at the instant it is being managed. In data processing, data is based on underlying data definitions. The definitions contain specifics as the data type. For example, whether the data constitute an integer, a string, or an array of other data, and an explanation of what the data represents. For example, bank account number or a street address. The actual data is an instantiation of the definition. It contains, for example, one particular bank account number or one particular street address. There is no difference in the case of management information. The management information in the MIB instantiates an MIB definition. The contents of the MIB definition are also referred to as a model. It reflects the type of management information being represented and constitutes a management abstraction of the real world. For example, a model that underlies one MIB definition might contain management information that represents the endpoint of a TCP connection. In the model, this management information has certain properties associated with it. Those properties constitute individual data items and could include items such as the TCP port number, the IP address, and port address of the remote endpoint of the connection, the number of packets that were sent over the TCP connection, and the number of packets that were received. Each property has its data type defined. In this section, we take a closer look at the models that MIBs are based on and how those models are defined. Of schema and meta schema. As mentioned in the previous section, the model that underlies the management information in a MIB is specified in a MIB definition. Some people call the model a schema, reminiscent of a database schema that constitutes the definition of the database tables. The underlying real world that is being abstracted by the model is often called the domain because it constitutes the subject domain that the model is all about. In the example of the previous section, the domain of the model is that of TCP connections. Confusingly, network management, often both the schema and the particular instant of the devices are called MIBs. In many cases, it is clear from that context what is meant, but sometimes it is not. As mentioned, a cleaner use of terms would be MIB for the instance information and MIB definition for the model or schema. Now we have established where the information in an MIB is defined, but an important part is still missing. The MIB definition itself needs to be specified using some specification language, sometimes also referred to as the meta-schema. The term meta-schema means a schema of a schema, a definition of how to write and interpret a model definitions. Figure 6 to 5 depicts the relationship between schema and meta-schema and model and domain. Quite a few MIB specification languages exist. Each of those languages is generally used to define MIBs that are used to be in conjunction with a particular management protocol. For example, the following: SMI and SMI version 2, Structured of Management Information versions 1 and 2. The MIB is specification language that is used in conjunction with SNMP. Manage Object Format or MOF, specification language that is used in conjunction with a management technology called Common Information Model or CIM. Guidelines for the definition of managed objects or GDMO used in conjunction with the Common Management Information Protocol or CMIP. today of only limited commercial relevance. Next, the impact of the meta-schema on the schema. In network management, the specification language constitutes the raw material out of which MIB definitions are molded by the MIB artist, that is, designer. Just as in the few fine arts, many different media, in this case, specification languages, can be used to create a valid model of the device being managed. Just as a watercolor of a dog looks different than a drawing of the same dog, the character of the model that results looks different depending on what meta schema is used. Figure 6.6 illustrates this. The following subsection discuss what impact the characteristics of a meta schema have on the resulting model, and what types of the meta schema tend to be popular by different purposes. And now, meta-schema modeling paradigms. Without going into details of real meta-schema, here are some examples of different types of specification means that different meta-schemas offer. One category of specification languages provides object-oriented constructs. This enables the designer of a schema to represent different aspects of the device as MO classes that can have attributes that can emit notifications. Existing definitions can be reused and refined by allowing MO classes to be derived from other MO classes that are more general in nature. This corresponds to an object-oriented concept that is known as inheritance. The derived class is also called the subclass. A class that is derived from is called the superclass. The second category of specification languages enables users to specify MIB definitions in the form of tables and variables that can be grouped in certain ways. A table refers to one particular aspect of the device, a class of MOs. So to speak, with the MO attributes represented by the table columns and instances by the table rows. Other specification languages might simply model everything as commands and functions and their parameters without actually specifying much of an explicit model. This, of course, is the case of CLI, the command line interface. Now we will tackle about matching management information and meta schema. Generally, management information that management agents on network equipment provide tends to be based on relatively simple meta-schema. This has to do with the fact that corresponding management agents tend to be easy to develop and do not require many processing resources, an aspect that is important for devices that, in many cases, are processing constrained. Number 1. State information is often modeled as tables and represented in SNMP MIBs because SNMP is the management protocol of choice for many monitoring applications. Then, logical configuration information is often managed using CLI, meaning that often it is modeled only in the form of parameters of CLI functions instead of a more explicit management information model. And last, historical information is often presented in proprietary formats, optimized for periodic retrieval in one large bulk file from a device. It is important to always remember that no matter what underlying metaschema is used, MIB is always a view of a managed device. Accordingly, it is also possible to have multiple simultaneous views of the same device. For example, you could have the same management information accessible via an SNMP, MIB, and via a set of CLI functions. Each view or each MIB can be supported by its own management agent, each interacting with management applications through a different management protocol. The different management views that the various management agents provide can have a different scope. That is, they can cover different aspects of the same managed device. They can simply complement each other, they can overlap each other, or one can be a subset of the other, as figure 6.7 is illustrates. Now, a simple modeling example. Let's take a look at an example. Imagine that you are tasked with finding a simple management log information model for a device. Figure 6 to 8 depicts an object-oriented model. In this example, a managed object class represents a managed system. It has three attributes to query management information: system name, system contact, and system uptime to carry the name used to refer to the managed system. The contact information of the group responsible for managing the system, the time elapsed since the system was last started. The management system is derived from a superclass, denoted by the line with the arrow, physical equipment, which has another attribute that managed system inherits, system location. Object of the class managed system can contain objects of another class, TCP connection, denoted by the line with the diamond. TCP connection has more attributes: TCP connection state, packet sent, and packets received. TCP connection maintains two different types of relationship to objects of another class. Endpoint, denoted by the simple lines labeled with the relationship names. Those relationships indicate which endpoint is local to the connection and which endpoint is remote. Object of the class endpoint contains attribute with the address and port information of the respective endpoint. And figure 629 depicts a table-based model. In this case, the management information is maintained in two tables. The table name managed system contains only one entry, including system name, system contact, system location, and system uptime as columns. The table name TCP connections can contain many entries. It has columns for local IP, local port, remote tel, remote port, connection state, packets sent, and packets received. The combination of the first four columns serves as a key for the table. That is, they are used to identify a particular table entry. The model here is a little more coarse-grained than the object-oriented one. For example, information about endpoints is not broken out separately. Figure 6 to 10 depicts a model based on a set of dedicated functions. Here, the managed system is modeled by three functions: show system data, show all TCP connections, and show TCP connection state. Show system data is used to retrieve information about the managed system. The function is defined so that it will return the name, system uptime, system contact, and system location when invoked. It is not necessary to define a parameter to identify the managed system because it is the system on which the function is invoked. Two other functions are introduced that allow a manager to modify the system name as well as system contact and system location information. TCP connections are modeled by the remaining two functions. Show all TCP connections lists all current TCP connections on the device along with their local and remote IP address and port information. TCP connection state and basic statistics of the number of packets that were sent and received over this connection. Show TCP connection state allows a manager to retrieve the TCP connection state of a particular TCP connection, identified by its local and remote IP address and port information. Note that this model is specific about how the manager accesses the information, which is model is eventually defined in a matter of design. Design is a creative activity. There is no single right way to model the underlying domain. Instead, different models are possible, some of which might be more appropriate and some less appropriate than others in terms of how easy they can make it to manage the device, how straightforward they are to implement, and how easily they can be extended and maintained. Now, the encoding management information. Finally, it should mention that management information needs to also be encoded when it is sent over the wire as part of actual management communication. That is, all the managed objects, identifiers, and values need to be implanted into a mutually understood representation that will fit into a management request or response that is exchanged between manager and the agent.